Hello, my name is DerekK, and this is my Lab 4 report for Physics 2211. In this presentation, I'll be walking you through my computational model of a string mass system oscillating in 2 dimensions. I'll explain how I gathered experimental data and the modifications I made to the starter code, and how I verify the accuracy of my model. The purpose of this lab was to investigate a system where a mass is attached to a spring and allowed to oscillate in 2 dimensions. The system involves 2 main forces, gravity and spring force. The mass can both move vertically and horizontally, so it behaves like a mix of vertical spring oscillation and a pendulum motion. Our goal was to compare real-world motion from a video data with a computational model and verify physics principles like conservation of energy and periodic motion. To collect motion data, I used the autotrack feature in Tracker. I loaded the videos, calibrated the scale, and placed a track point on the mass. Autotrack gave me the x and y positions of each frame. I exported just the x and y coordinates into a CSV file, which I later read into VPython code to compare against my simulation. I changed the system mass to 0.402 kilograms. I used the tracker data to set the initial position and estimate the initial velocity. I did the spring constant to 6.88 Newton meters and the relaxed spring length to 0.127. I corrected the stretch formula, which is the correct way to calculate the spring length by doing L minus L naught. I fixed the spring force direction, making it restorative, and properly calculated the kinetic energy using the squared speed. The system in this model includes the mass and the spring, while the surroundings include everything else, which we assume has no influence. The only forces considered are gravity and the spring constant. There's no friction or damping in the model. This assumption allowed me to test the system as an isolated one where energy should be conserved. I modified the spring constant to 6.8 Newton based on the system's characteristics. The relaxed length was set to 0.127. For the stretch of the string, I updated the equation to S equals magnitude L minus L naught to correctly calculate how far the spring was displaced from its rest length. This graph shows how the model's predicted motion in blue compares to experimental motion tracked from the video in red. For both the x and y position, we can see a good alignment in oscillation frequency and general rate, which suggests my model is accurately simulating the motion of the real system. One of the key goals of this lab was to test whether the energy principle is satisfied. The energy plots show how kinetic, gravitational potential, and spring potential energy changes over time. Even though each individual component fluctuates, the total energy remains nearly constant. This confirms that the system conserves energy, consistent with an ideal isolated system and Newtonian mechanics. To analyze the periods, I looked at the time between successive peaks in the tracker plot. The x direction period was slightly longer than the y direction period. This makes sense because the horizontal oscillation is less affected by gravity, while vertical motion is influenced by both spring tension and gravitational pull. These differences highlight the coupled nature of the 2D oscillations. I implemented the code to calculate the kinetic energy using the square root of speed, gravitational energy using the y position, and the spring potential energy using the spring stretch. At each time, I calculated how these energies changed, as well as the total energy of the system. These were plotted to visualize how energy transformed from one form to another. In my model, the energy principle was satisfied overall. As the mass moved, kinetic, gravitational, and spring potential energy changed continuously, which is expected during oscillations. However, when looking at the total energy plot, the total mechanical energy remained nearly constant throughout the simulation. This confirmed that the energy was conserved as predicted by physics. Any slight fluctuations in total energy were likely due to rounding errors in the numerical calculations or small measurement inaccuracies from the tracker data. One main source of error was how I recorded the initial data using Tracker. Since I began tracking slightly after the motion has already started, the first few frames may not represent the true initial position and velocity. This likely caused a mismatch in the early motion and contributed to some drift in the energy graphs over time. Additionally, auto-tracking also isn't perfect and may have introduced small inaccuracies in the x and y values frame by frame. Despite these limitations, the computational models still follow the experimental data closely, showing how useful physics-based simulations can be when properly calibrated. Thank you.